right. And it's using the correct microphone, and I will mute these folks. All right. And let me try and turn off my noise here. There we go. All right. And I think I'm going to make this brighter in hopes I can see it. There we are. All right. So here we are, 129. Anyway, we got about 8 minutes before the official start time. So let me start with the news, which there is always a ton. So let's see. This is pretty interesting. And in fact, this is pretty awesome. And that, lots and lots of good stuff. This is probably one of the most important ones. A lot of that stuff is nonsense. All right, so let's, so we tried to FaceTime last night. Caitlin was listening to my phone. We couldn't get the video off my phone, but she totally got the audio off my phone. And so apparently today, Apple has taken the whole service down. I haven't tested this, but that is a very wise move. If you have a god-awful vulnerability and you have no patch, it would probably be a good idea to just turn it off rather than let everyone get hosed and deal with the lawsuits and such later. So this is kind of mind-boggling. So Facebook wanted to know what people were doing with their phones, so they pay you like $30 a month to install a VPN app which sends all the data from all the apps on your phone to Facebook for analysis. And this is selling all over the place. And this has been around for months. And apparently Apple caught on to this and decided it was illegal and blocked it. So Facebook rebranded it, outsourced it through another company to pretend it was somebody else, and did it again. And I got the app. I went online and found it, but it wants an activation code, so we're going to have to hack it to turn it on. But this is awesome. I got to take this app apart for the mobile device hacking class. Let's see what it does. That would be awesome. Anyway, so this is real. I got the app. I found all the codes from like 6 months ago of people saying, you can install this and you'll get $30 a month. This is great. And how to sign up and everything. This is just mind-boggling. Anyway, that's the game. Apparently this app has total access to everything. Facebook Research was the original name. I think they might have changed the name to something else, but I got the original Facebook Research one. So this is pretty mind-boggling stuff. And this is a whole new level of hell. So you have all these Internet of Things devices. Now your light bulbs are smart. Now your light bulbs connect to the Wi-Fi. Well, it has to remember the password. So it stores the password in plain text on the light bulb, and you can steal it from the thrown away light bulb, which in retrospect, we should have seen this coming, but that's pretty awesome. So I totally got to get some of these bulbs and try that. That sounds swell. As a matter of fact, it's not incredibly obvious what else they should do here. I guess they could hash it or something. You know, if you have credit cards now, they generate these one-time use codes. I guess your Wi-Fi network should generate one-time use codes for the bulbs or something, but then now the bulb has to keep reconnecting day after day. I don't see an immediate answer here without a lot of work. Anyway, Mark Zuckerberg has announced that consumers love Facebook targeted ads and they think it's swell. This is like Trump just announced that nobody minded the shutdown. The government workers are grateful they didn't complain at all. This is the ancient strategy of the big lie. And so there's some real researchers went and researched people, and they found that in fact, like 85% of people do not want targeted ads if you explain to them how it works, that they're spying on everything you do to target them. Now, if you just tell them you're seeing ads on topics of interest instead of boring ads, then about half of them will go for that. But if you explain to them how it works, they don't want to go for it anymore. And, you know, that's not too surprising, I think. In Facebook's defense, I would say that someone needs to pay for the web. And if you're not going to pay like a penny for every email and half a cent for every page view, they have to get money somewhere. And targeted ads is our current dodge to get it for free. Anyway, so we'll have Dwayne Johnson running for president. I think, I guess why not? Everybody else is. Oprah wouldn't, but that's probably because she's smarter. But anyway, Dwayne's not ruling it out, so maybe he'll be the next president. If not him. I'm not calling myself out either. Well, there you go. And if it might be the guy running Starbucks. He's going to apparently run. So.
We need more billionaires
Apparently we do. Well, you know, as a fundamental principle, I think everybody that wants to run should run, but hopefully the voters will laugh at most of them and settle on someone reasonable, although I must say the last election doesn't bode well for that theory. So there's the fake stake attack. This is more details about an attack I saw a few days ago. So if you have a cryptocurrency network using proof of stake, that means you basically are betting some of your money on your mining. But what you can do is you can mine a bunch of fake chains, and the miner devices that have to verify whether you have in fact mined the next block have to investigate all the chains. So by generating many spurious chains with no real stake in them, so they have no chance of being right, you can perform a denial of service attack where the other miners are wasting all their CPU, checking all your bogus threads, and now you're more than 50, 100% of the power, and now you win. It's actually pretty awesome. And this has happened to many, many protocols like SSL and other protocols that they make something complicated and usually cryptographic, and then there are a bunch of denial of service attacks that involve bombarding you with stuff that you have to encrypt or decrypt to where it uses up all your CPU, and I can get away with murder while I tie you up with that. It's an interesting attack. And another thing that's true here is he pointed out that there was originally Bitcoin. Almost all cryptocurrencies are just copies of Bitcoin with a few changes. One small coin invented proof of stake, and almost all of them are copying the code from that one coin. So this is what tends to happen. They're pretty much all just clones of each other. And none of this code has really been audited properly for security. The only one that has any real argument that it's secure is Bitcoin, because it really has been around for a while and been attacked a lot. But its security model does not extend to clones of it, because it depends on having the fastest computer in the world doing the mining. So it is a very strange thing to put large amounts of money in something that is so manifestly untested, unproven, thrown together in a hurry, and so on. But of course, people see opportunities for growth by being the people that will jump in where a more conservative person wouldn't go. So the US has indicted the CEO of Huawei, in addition to a previous Huawei executive they arrested, and this time they explain what they're mad about, and this is pretty important stuff. So the founder totally lied to the FBI. Ren Zhengfei, that's her. Apparently, I had a picture of her in the other article, something different showing up here. Anyway, she told them she'd complied with all export laws, and they were totally exporting things to Iran in violation of U.S. sanctions, and lying about it, and claiming that someone else resold their stuff there when it was in fact a subsidiary of their company, which they used as sort of transparent shell game. And so the next thing they did was steal trade secrets. The surprising thing is the trade secret. This was in the last article too. The ultimate trade secret they stole, which is causing a huge trade war between the countries, was Tappy, a robot that taps on the keys of cell phones. I would have thought it would be an atomic bomb or flying car or something exciting. It's Tappy, the proprietary product developed by, I think, Verizon to test their phones. And they snuck in people to like carefully steal some of the boards out of Tappy and clone them at night and bring them back. And there you are, the T-Mobile's Tappy. This is the thing that ignited the giant war. They cloned their robot that taps on keys. And that's the game. So anyway, we will see what comes of it all. We are now indicting people in a foreign country. That means they can't come here. I don't really think they're going to go bring their bin from China, but we will see what comes of all this. All right, and it's now time to just carry on with the usual stuff. So a schedule. This is 141, and so this week we are going to talk about Chapter 2, which is randomness. Then there's no class next week, and the cryptographic security is on February 12th. So let's talk about randomness, which is a very exciting topic. This is, among many other exciting things about it, this is the main way the NSA spies on you, which we'll talk about, which they somehow skipped in your book, but I filled that in. So the author of the book may possibly have been somewhat averse to controversy. Anyway, so we'll talk about what randomness is, and then what probability and entropy are, which are the mathematical ways you measure randomness. And then we'll talk about the various types of random number generators that are being used in your computer system and how things go wrong. So if you have a random number generator like Dilbert does, and it tells you 9 6 times, then you would like to think that's not very random, but you don't really know, because that could happen. Like if you're rolling dice, it could really give you the same number several times. So what does that mean? And that is a huge problem. If you show people a pattern of bits like that, they feel like that's random, and 0000 is not random. And that's because it's going into the human brain, and you see that first number not as 1101, 0110, the absolute value, but it's natural to interpret it as a number with 5 zeros and 3 zeros and 5 ones. And if that was all you knew, that would in fact be a large category of numbers, which is more likely than all zeros. And this is closely related to the gambler's fallacy, which is a very common thing. Gamblers bet on things like a roulette wheel, and then when they win 3 times, they think, I'm sure to lose now, to make it come out even. But of course, their chance of losing is the same every time. It is a human psychological thing that you're keeping track and assuming that any measurement of like 5 in a row should come out even. That is totally not true. But it is a feeling humans have that I pressed my luck enough, it's going to turn, or I'm having a hot streak, I can bet more today. You're the one that sees trends in things, but if it's really random, there are no trends. There is no pattern. Each roll is completely independent. And that is very hard for humans to understand because humans don't live in a world where that is how it works. The way it works here is if you step in a tar pit and you get out, you want to remember never to go there again. And if you escape from a tiger, you want to remember to run from everyone you see. Humans have this thing called single trial learning because the natural world presents us with dangers or one experience we should learn from. You do not go repeat something 100 times to get statistics to see whether it's really dangerous. But that's what you'd have to do for random numbers. They're very unnatural, and human intuition tends to mislead you about them. So here's probability. If you flip a coin, you have a 50% chance of heads and 50% chance of tails. If you roll dice, you have 1/6 chance of each of the 6 numbers. So those are uniform distributions where you have a series of options and you have the same chance for every option. So you measure that with entropy. And entropy is a physics term from thermodynamics, which is kind of abstract and hard to understand. But we're talking here about Shannon entropy from Claude Shannon. And this is very easy to understand as information content. And that makes it very easy to remember. So if you have a distribution with probabilities P1 through Pn, the entropy is mathematically this, minus P1 log P1 minus P2 log P2. If you're familiar with logarithms, this is how you actually calculate it. If you're not familiar with logarithms, you don't really have to learn very much about logarithms to understand this if you think about it as information content. So if you have 1 bit, you have a 50% chance of a 1 and a 50% chance of a 0. So the entropy is minus 1/2 log a half minus 1/2 log a half. Now log to the base 2 of 2 is 1 because you take 2 to the 1 to get 2, and log of a half is minus 1 because you take 2 to the minus 1. So that is 1/2 of minus 1 and 1/2 of minus 1, and that adds up to 1 bit. And in fact, anybody would have told you if I have one number and it has a 50% chance of being 0 and a 50% chance of being 1, then the amount of information it has is 1 bit. That's kind of obvious. And so if we have a random byte, 8 bits, then our 256 possible values, each one of them has a probability of 1 in 256. So if you run the math, you take 1 over 256 times the log of 1 over 256, and you have 256 such numbers. So you end up with the log of 1 over 256, which is minus 8, because you have to take 2 to the minus 8 to get 1 over 256. So you have 8 bits of information if I give you 8 bits of data, and that is just what you would think. So, all right. And if you have a non-random bit, 100% chance that it's 0 and a 0% chance that it's 1, now the entropy is 0. As you would think, there is actually no information in that. It's just a 0 sitting there. It's not like it had a chance of being a 1, and now you know something because the real value is 0. It was always 0. It's like painted on the wall. It doesn't convey any meaning. And that's the more precise analysis of the thing that was in the first slide, where we say if you're just getting 0 every time, you have a feeling that this is not random. This doesn't really contain any information. And if you were to take a file that just has a capital A 1,000,000 times and zip it, it'll zip down to almost no size because it's very easy to describe that in very simple terms, 1,000,000 times A. It does not have 1,000,000 bytes of data in it at all. It's got the same byte repeating, and it's very easy to, so there's really not much information in that file. So you can do this stuff in Python. So let's play with it a bit. Let me bring up my Python code. All right, and if I blow this up, it's here. Okay, and so I've got entropy 1, so let's take a look at that. If I nano entropy 1. Okay, so I've imported math. The only reason I had to do that was to get logs. And you can have math.log of a probability to the base 2. You can do math, the logarithm to any base. And for Shannon entropy and the kind of stuff we're doing here, information content, we want to think in terms of bits. So everything is to the power of 2 and the log of 2. So I take a probability distribution. This is the coin, 50% chance of one and 50% chance of the other. And so I'm just going to print out the probabilities, and then I'm going to do this calculation. Start with 0, and then take minus p times log of p for every value of p in the probability. That's all this loop is going to do. So if I run this one, it gives me the entropy is 1. I have 2 options with a 50% chance, and I have 1 bit of entropy, just like you might think. So let's take a look at the next one. That's here. Now I've got 8 options, each equally probable. So how many bits does it take to do this? How many coins would it take? Not 8. If I had 8 coins, how many possibles would there be? I was confused too when I did this the first time. But if you have 8 coins, how many possible combinations of heads and tails are there?
3 coins.
That's right. She's got the answer, but it's 256 if you have 8 coins. This is 3 coins. 3 coins, you have head, 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 tail, head, tail, tail, head, tail, head. There's 8 combinations. So this is 3 coins or 3 bits. And so I am going to add those numbers. And so if I run this, this is entropy of 3. That is 3 bits of data because I have 8 possibilities. The third one is the one that is probably more obvious, which is, this is the weighted coin. Right. So now suppose I have a coin that is not fair. It does not have a 50% chance of 1 and a 50% chance of 0. It has a 90% chance of 1 and a 10% chance of 0. How much entropy do you get now? Well, what you get is half a bit. You have to have less than a bit because if it was even, you had 1 bit. If it was 100% of one option, you would have entropy of 0. You're in between. It's about half a bit. And if you want a more extreme example, the last one was 99% or 99.9% of one and 0.001% of the other, or 0.001, therefore 0.1% of the other. So only 1 chance in 1,000 of the other option. And if you calculate the entropy for that, it's almost 0, 0.01 bits, which is what you would expect. You're getting close to a sure thing, and a sure thing has no information. It might as well just be painted on the wall. So those are some examples of entropy. And by the way, how to do these simple things in Python, which we're going to do in all the projects in this class. With just a few lines of Python, you can do any of these cryptographic things. And that's what we're going to be doing. All right. So I've got a few Cahoots about that stuff. Let me bring them up. I think I have my Cahoots open someplace. Here they are. And this is 2A. There we go. And I'm randomizing the answers. Good. There we go. I get 8 people online and maybe 6 in the room. Better wait a little longer. All right, guess I'll wait another 5 or 6 seconds to see if anybody more is coming. It may be that all the remote people have gone to sleep. Apparently so. All right. All right, what's the log of 1/4? Okay, -2, because 2 to the -1 is a half and 2 to the -2 is a quarter. All right, what's the entropy of 1 random bit? One bit of information How about a random byte? Okay, 8 bits in a byte and 8 bits of data in a random byte, 8 bits of information. All right, how about a single base 64 character? Okay, base 64 is where you take 6 bits and encode a character because you use only certain letters. You use lowercase and uppercase letters, numbers, and then 2 symbols like slash and plus. And so there are only 64 possibilities. So you're only using 6 bits. That's 6 bits of data in a base 64 character. That's why it takes 4 characters of base 64 to encode 3 bytes. And it's used to encode binary files for email. Anyway, an unpopular answer, but it is 6 bits. And we use this in malware analysis in a lot of places. All right, so let me record the winners. And it looks like we can just keep going. It's not too late. So I got Ming and Caitlin. And Chris Clark, looks like a real name too. Good. All right, so let's go back to here. All right, so here's random number generators. And there are several related types of random number generators here to use for different purposes. So the main ones are RNGs and PRNGs, the random number generators that are really random, and the pseudo-random ones that are mathematical and not really random. So to get something really random, computers cannot do it, at least before the Ivy Bridge, because there is no component in there that is random in any way. It's all ones and zeros, it's all deterministic. So the only way a computer can do it is by reaching outside the computer and getting some source of entropy elsewhere, from something like network traffic, or the user moving the mouse or the keyboard, or some kind of sensor detecting something that it can interpret as random. And it calls that a source of entropy and tries to build an entropy pool from it, which is random stuff it can use to generate random bits, because that's the fundamental problem in computers. They're supposed to be just 100% deterministic, flipping bits in a certain pattern, so there's nothing random there. And so that's what random number generators do. They read real randomness somewhere. Then after you've got a pool of random bits, you use a pseudo-random number generator to mathematically calculate a stream of apparently random numbers with the data entropy used as sort of a seed, just to get it started. So real randomness comes from things like temperature, acoustic noise, electrical fluctuations, key presses, things which the computer interprets as random. And of course, they are not perfectly random. Correct randomness is sort of an impossible philosophical thing, but we treat them as random. You get them as random as you can. There is something that's probably about as close to perfect random as you can get, which is a quantum random number generator, where you take a quantum event like a radioactive decay, which as far as anybody knows is very random and unaffected by external things like electric field and pressure and temperature. So that would be about as close in the world of physics to something perfectly random as you can get. Yeah?
So when I was teaching fifth graders, I actually used a quantum random noise generator for a game. And,
yeah. They had it?
Well, yeah, you can go online and you can
Okay.
quantum random number generator.
Oh, good.
And but the thing that kind of scared me afterwards is I was reading some interpretations of quantum mechanics, and your field is physics.
Yeah, yeah.
And every interpretation of quantum mechanics seemed to indicate I did something very bad to the universe by essentially changing the entire outcome of the entire class by reading numbers from a from a radioactive decay.
Well, there are several interpretations here. See, Einstein started it all because quantum mechanics has things that are random. And this really offended Einstein. And classical mechanics does not allow this because everything is deterministic. And so this is where you get people that say there's no free will. If you believe Newtonian mechanics, then all the atoms are moving like billiard balls, bouncing off each other, and therefore you can predict the future, and therefore you have no choice. Our atoms are moving in a certain direction, and they will just continue to move in that direction, and nothing can change it. And quantum mechanics, though, shows that certain fundamental measurements are really random. They're unpredictable. And so Einstein's interpretation was that is not possible. God does not play with dice. What's happening is there must be a hidden variable that is making it look random because you just haven't done your measurement carefully enough. There's something you forgot to measure. And in principle, it's all still determined. And that is still arguably an open question in the world of quantum mechanics. And that's one interpretation. which would mean the world really is deterministic and all the apparent randomness is just an illusion. Another interpretation, which I think is getting close to where you are, is the many worlds interpretation, where every time something happens that could happen two ways, the universe splits into two, and you go down that path, and there's an infinitely expanding bunch of paths, and that's one option. Another one is the collapse of the wave function, which is what you're saying, where after you make a choice, all the others are gone, and this is the only one that persists. But in a way, this is just, it's all about cause and effect. And so there's nothing special about the random number generator. It is absolutely true that when you have a room full of kids and you do things, you change the future with the decisions you make, and now you're on a different track than you would have been if you made some other decision. At least that's what we think, because we appear to have cause and effect, and therefore we assume we have human responsibility, and it matters what choices we make because the consequences result. These are all hypotheses, and you can't prove any of them. And in quantum mechanics, you get right down to the bottom of this. You know, is there any real choice in the world? Is there really any cause and effect? And, you know, you get, that's why if you do physics far enough, it turns into the same thing as philosophy and the same thing as religion. They all get right down to the very basics of what's going on here anyway. And the real answer is we don't know, but there are various competing models. Anyway, so then you got your pseudo-random noise generator. Once you take one of those things, like quantum mechanics or the microphone or the keyboard or something, and you get some pool of numbers that you regard as really random, then you want to make a long string of random numbers from that, and you use a pseudo-random noise generator. And the point of this thing is it scrambles the bits from your pool of real entropy to try to make sure that all the patterns are removed and you get a long stream of bits. That's the plan. Even if you don't have a lot of real entropy coming from the world because, for example, you're a headless server and there's no mouse connected, so there really isn't very much happening for it to read entropy from, this pseudo-random noise generator has the ability to keep pumping out bits that will look pretty random, even though they're actually not based on very much original randomness. And so that's the game. It gets the pseudo-random number generator gets bits from the random number generator, and it updates an entropy pool, and then it uses the entropy pool, and it makes some attempt to figure out when it's used up the entropy in the entropy pool and it needs more entropy. So this uses a deterministic random bit generator, which is what can take some bits and create a chain of data. And this always produces the same output given the same starch. It's deterministic. That's what I mean. Nothing random about it. It's just a way of taking a small number of bits from the entropy pool and turning it into a long chain that is not obviously connected to those bits. So it has an init operation that starts it off. So this loads the entropy pool from the random number generator that really gets it from some kind of external source. And then it sets up an internal state because the pseudo-random number generator does have some internal registers. That's how it remembers where it is, and that's why it's deterministic. If you start it from the same initial state again, it will produce the same series of numbers. So then it refreshes, this reseeds it, getting fresh entropy, and then you have next that just gives you the next bit in the current chain. And this, of course, is really important for cryptography, for example. In a way, all cryptographic routines that are based on a key are like this. You have a deterministic, apparently random stream that's generated from the key, and you use that to encrypt the message. And then the person at the other end has the key, and they create the same string of apparently random bits. This is what we were saying in the last class when people said, why don't we use the one-time pad? I'd say essentially we do, except it's too hard to deliver the one-time pad, so we use this kind of system where we deliver a key, and then we generate a long stream of apparently random bits from the key, which is like a one-time pad, but not as secure. Anyway, that's the game here. So if you wanted to decide how secure this is, there are two things you might want. Forward secrecy means you cannot take the current value of the random numbers and deduce what the previous numbers were. That's forward secrecy. And the prediction resistance is the opposite. You cannot take the current set of numbers and predict what numbers are coming next. You want both of these properties for cryptographic security. If either one of them is violated, then you have a weakness in your cryptographic system. And this is what the US government is exploiting. We have a gigantic center in Utah run by the NSA, which is archiving all the data that they've been taking ever since 9/11. Shortly before 9/11, the US government made a secret deal with AT&T, completely violating the Fourth Amendment, to copy all the data on the internet and all the data on the phone network and archive it. And they have been doing that. And about 10 years later, when it became public, it was declared retroactively unpunishable. AT&T was given a pass because they cooperated with a government request, even though it was certainly illegal. But people regard it as an emergency because of terrorism. So they're archiving all this data. Now, what's the point of archiving all this encrypted data they can't open? The point is sometime in the future, they're hoping they will hack into a server and steal the key, and then they will calculate all the previous keys, and they'll now be able to decrypt all that old data based on the key they get in the future. And the reason they can do that is because until Snowden's revelations a few years ago, about 2012, nobody bothered using encryption routines with forward secrecy. They all use TLS 1.0 or 1.1, which do not have forward secrecy. They just use the public key from the server forever. So if you ever get a private key from the server is what you need to open it. If they ever get the private key, they can go back and decrypt all your Gmail from years ago with that key. And because of the Snowden revelations, everybody jumped up to TLS 1.2, which uses a different key for each transmission, and that will mess up this plan. You will have to separately steal the key for each message. You will not be able to take one master key and get in at all. And there it is. These two buildings in the middle are the giant warehouses storing huge amounts of data. And on the right is the power and so on. This is the giant center that is archiving all that data and hopefully hunting through all that data. And of course, from the viewpoint of law enforcement and espionage, somewhere in that data are all the terrorists, all the spies, all the drug deals, all the arms deals, if you could only find it. Everything that happens on the internet or the phone network is in there somewhere. And there's a bunch of people trying to write data mining algorithms for the government, trying to find things in there. So backtracking resistance, if you want that, that means refresh and next must be irreversible, so that even if you learn the current state and get the whole entropy pool, you can't predict what happened in the past. And prediction, or can't deduce what happened in the past. And prediction resistance, of course, means the refresh must add fresh randomness in so that you can't predict the future from the current state. Those are desirable properties of your random number generator. So one of them is Fortuna. By the way, Bruce Schneier, I mentioned it before, his blog is great. He's a wonderful speaker. He writes good books, and he's a very serious cryptographer. He invented many of the random number systems that we're using today. He's very good at this. So he wrote Fortuna. And this is what Windows uses. It has 32 entropy pools, a 16-byte key, a 16-byte counter, and it has a system to create this stuff. Mac OS and iOS use the previous one from Bruce Schneier from '98 called Yarrow. I don't know why he updated to Fortuna, but apparently Yarrow is not so terrible because Mac OS still uses it. They both are similar. And so here's things that can go wrong. If you don't produce enough random bits, you don't have enough data coming in from whatever the external source of randomness is, Fortuna might not notice this, and therefore it might produce lower quality pseudo-random bits. Or even stop delivering bits, if you somehow steal the seed files or reuse the seed files because you allow multiple threads to be accessing the random number generator at the same time, and you somehow end up with a mistake where two of them use the same seeds, then of course you're going to produce identical sequences of bits. So these are possible things that can go wrong. So there are two kinds of random number generators in general. There are cryptographic ones and non-cryptographic ones. This is a problem. The original reason people wrote random number generators was for simple things like games, where they just want to have enemies attacking you or something. And so all they cared about was a certain kind of statistical purity where if you take a lot of samples, you'll find them evenly distributed. And they won't find any patterns in there any more frequently than you should. And that's all they cared about. They did not think about forward or backward predictions. All they thought about was those statistical properties, and they designed statistical tests to test for those. And they invented things like the Mersenne twister, which create things which satisfy the simple tests for randomness and are usually what you get if you just call the random number function in your programming language. The problem is they are not unpredictable enough for cryptographic use. So you have to get cryptographic pseudo-random number generators if you're going to use them for cryptography. And here's the real world ones. dev-urandom is the one that is recommended in Linux. This is non-blocking. It will always return data even if it can't find much entropy. Dev-random is the older one that is blocking. It will not return anything unless it can find enough entropy in the raw entropy source. And that is interesting. That sounds like a good idea, blocking, but it turns out to be a really bad idea because your calculation of how much entropy you have is in fact very unreliable. So it's in fact pretty easy to trick dev-random into thinking it's out of entropy when it's not, and create a denial of service situation. So in practice, you're better off to just use dev-urandom that will just keep creating apparently random bits the best it can with whatever entropy is available. And there's a lot of weird things, and here's something I wanted to show you because this happened to me. I've showed up a Tomcat server to run a security game I was running, and it took 45 minutes to boot up. And I Googled and I said, what's wrong with here? And I found a bunch of people explaining this. This is absolutely true because you don't have enough entropy on the server, and the Java-based Tomcat will not start until it has enough bits to create the key. So you have to install haveged, will create a lot more entropy faster using a special thing called the have-get algorithm. Some people argue that the have-get algorithm is not producing data that is as perfectly random as it should, but it produces a lot of it fast. And it causes the processes in the machine that are freezing up for lack of entropy to move faster. And in practice, when I did it, my server went from booting up in 45 minutes to booting up in 10 seconds. So it really matters. And you can see it, which I thought is awesome. So let's give this a try. You can do it in your Kali Linux or any other Linux. Let me get my Kali Linux up. And there it is. Okay. And I'll see, okay, here, that's all set there to go. We can see it in that little window. And I don't have VMware Tools working very well, which I thought was actually better for this demonstration, because if I drag the window bigger, it will just stretch, and that'll probably look better to the people in the video and stuff. So where's the edge of my window? Here, window. There's one edge. Maybe that'll do. Come on, stop messing with me. Right. My brilliant idea is not working out so well. There we are. I finally got hold of a corner. There we are. Now I feel better. Okay. And now it's, no, I can deal with, I cope with this. Let's go Control C. I said Control C. There, let's do this. Now it's going to work. Shift Control Plus. There we are. I can defeat this thing. For some reason, VMware Tools is going to work right now. VMware Tools is pretty random on Kali. All right. So what I'm going to do here is run this one-liner. For I, going from 1 to 100, it's going to print out this number, procsys kernel random entropy available. That is the entropy pool size in bits. It's just a system variable, and you can see it. So it's going to print it out every 2 seconds. So I have 1146 bits of entropy. And as you can see, it's somehow harvesting a couple of bits here and there. Now, if I flip back and forth and I move the mouse around, it should get more entropy. Yep, there's 1176. And I think if I drag this window around, it'll go up even more, 1184, 1193. So now I'm creating entropy, and it's seeing it. So that's pretty cool. I could also deplete the entropy. Here's the command that does that. This will read a bunch of dev random and then print it out in base 64 so we can see it. It's going to read blocks of 8 bytes and 8 of them, 64 bytes, and print it out in base 64 so I can see it. So if every time I run that, it's going to use up some entropy. So that 1207, you didn't see much happen there, but if I do it really fast, it goes way down to 399, and now I actually get partial read. Dev random has refused to give it enough data to do this. All the entropy in the entropy pool is gone. I've used it up, and it's taking a long time to get it back. And dev random doesn't give me enough data, the amount of data I asked for, because it can't find it. Remember, it's the one that has blocking. So that's pretty awesome. And the next fun thing is let's put on have-get. Because have-get is just in the Debian repositories. So I can apt install have-get. Okay, and there it goes. Yes, yes. My entropy is recovered up here, 2419. Okay, yeah.
So is it using like latency from the network to also increase entropy? Is that?
I don't know where it gets it, but I think have-get is not that it gets more. Yeah, I think it's getting network transmission. Yeah, that's where it's getting some, and also the mouse. You're right. Anyway, so now that I have have-get in there, my entropy is up to 2400, and if I do the same thing as before, where I just dump a bunch out, it goes down. Come on, stop messing with me. There we are. It's down to 1900, down to 1400. And I can do this as fast as I want, and it comes right back up. I now have a lot more system entropy, and I can't use it up anymore. Because have-get pumps out lots and lots of bits into the entropy pool as fast as you want them. And the mathematicians will say it's not perfect, but for most practical purposes, this makes your server run better. And that's, of course, the thing we're going to see everywhere in security. Doing it right is almost always too much bother, so you do some sleazy approximation of right to get the job done, and then there are risks. But not having any product is a risk too. So you have to find a reasonable compromise between actually getting something done and getting it done right. Anyway, so I thought that was fun. And let's go back to here. All right. So Windows has its own version of all this, which is, of course, more complicated because Windows is almost always more complicated, but it's the same general principle. You got crypt gen random, and now they've replaced it with bcrypt gen random. As they'll do hash functions later, but bcrypt is a more precise hash function than the older crypt, so it's probably more perfectly random. Let's see, regarding Fortuna, Are the what can go wrongs actually documented incidents? I think they are based on documented incidents, but I don't really have the references where they talk about using the same pool the same data more than once. It's a good question, and I don't know the answer. Anyway, all right. So, let's see here, another chat message coming in. Let me see. Okay, great. All right, good. So, anyway, here's Windows, and they have, it takes entry from a kernel mode driver, which had a previous name, and basically using Fortuna. So it's a similar process, but I didn't find an easy way to set up the same demo on Windows. I might struggle with it another day. But anyway, so then there's, of course, a way to go forward. Like I said, the reason all this nonsense is necessary is because there's no actual source of randomness. And there's no real reason that there isn't. You could have one. And Intel did this in 2012 in the Ivy Bridge processor. They added a hardware random number generator. Now, a hardware random number generator is easy enough to make. You just have a resistor and you run current through it, and then you amplify the current until you see the noise in the current. And then the noise, if you have a battery and you connect it through a resistor, the current should be constant, but it varies because of random thermal motion of the atoms, which causes it to have a little more resistance and a little less resistance. So there's a source of random noise. And they made a hardware component that makes hardware random numbers. So they hopefully thought they were going to put an end to all this. The problem is Edward Snowden. Edward Snowden had just revealed what we're going to see, really horrifying stuff about how the NSA is lying to us and poisoning the random number generators. And the problem with the hardware random number generator is you can't audit the code. You don't really know how it works. You can't tell how it works. You don't know that the NSA didn't poison it. You can never prove that, so a lot of people refuse to use it, just assuming it's probably poisoned, and they'd rather use some kind of mathematical routine that they can test. And you could argue that. So that's the game, and here's what led to all this. Microsoft started up with Neil Ferguson, who, by the way, is the guy that worked with Bruce Schneier. He gave a talk in 2007, and these are the real slides from his real talk in 2007. The Microsoft researchers found there might have been a backdoor in the National Institute of Standards recommended random number generator, which was based on elliptic curve cryptography. It's this SP800. If you use any kind of military documents, you're always referring to these SP800 documents that are the official military recommendations for networking and cryptography and security and such. And if you want to sell any software or hardware to the government or the military, you have to be compliant with the official military recommendations. And this was their official recommendation for a random number generator. And they went through several slides with mathematical details, and then they said, we're not saying that they deliberately poisoned it. We're just suggesting maybe they made a mistake in their cryptography. But it seems like this stuff could be predictable if you know the numbers from which it was made. And then Schneier at the time said, you know, another thing that's very strange is that this thing they're recommending is 1,000 times slower than other algorithm that seems just as good. And the NSA is really, really pushing it vigorously and forcing people to put it in and demanding it, make it the only good standard. When there's no mathematical reason for that. And it makes you wonder, why do they push this weird thing so hard when it just seems to be bogus? And then Snowden leaked out the top secret documents that are here, which proved that it was in fact a deliberate government plot. And this is pretty damning. Here's the top secret document for, not for display, of SIGINT enabling. This is where they plan millions of dollars to be spent to prevent people from using good cryptography and deliberately lie to them and trick them into using broken cryptography. And here's from that top secret document. They actively engaged the US and foreign industries to covertly influence their commercial product designs to make them exploitable. This is what everyone thought they did because of the DES algorithm, where they strangely made it weak. Down here, they inject vulnerabilities into commercial systems, and they influence policy standards and specifications to make the official recommended standard things weak so they can hack in. Now, this outraged the security community so much that they wouldn't have any feds go to DEF CON. They said they couldn't guarantee your safety at DEF CON. The hackers of the world were so angry at the government. There is another side, of course. The official mission of the NSA, as far as anybody knows, is to spy on everything. That is their job. They are supposed to find a way to perform no bus, nobody but us. They are supposed to have a backdoor in everything so they can read it, but nobody else. And Bruce Schneier said at a talk I went to a few years ago, he said, if you wanted to accomplish no bus, poisoning the random number generator is probably the best way to do it, because nobody would ever be able to detect it. And if you don't lose the secrets, nobody would be able to reproduce it. And it would have the effect you want, that you can get in, but nobody else can get in. And that is what they are supposed to do. And they are the smartest people in the world with essentially unlimited resources, so it's not all that surprising that they are doing it, but this really bothered people. And so this is like we talked about the fundamental nature of reality. Is there such thing as cause and effect? There's another huge fundamental thing. We have these moral principles of our society, and every society has a black ops team that breaks those rules. They always have, and you have a fundamental conflict where you pretend to have these values, but you do have a team that breaks those values. And if you don't, then somebody else nastier will wipe you out. And so all your principles only go so far. And that messes up the kind of people that like to see purity. Anyway, so the NIST in 2015, what's 8 years after all this scandal came out, they officially changed the standard and say, well, okay, you better quit using that thing. Basically, I think they found that it was impossible to make people keep using it because the secret had come out. And this is the third or fourth time they have absolutely been caught trying to force us to use something that they knew was broken. And that's why a lot of cryptographers have got this bad attitude where they will not touch anything that is approved by the government. They'll only use other things. And if anything is approved by the government, they assume that means it's backdoored. And I don't know if it's justified to be that cynical, but a lot of cynicism is pretty justified. They have been caught red-handed several times, so you can't say that that's totally stupid. Anyway, so here's other ways things can go wrong. You could have poor entropy sources. Netscape did this. Netscape needed to have some sort of random number, so they just took the process ID and the system time in microseconds to get a number that looked random. And of course, in the infancy of encrypted communications, the first version of HTTPS, this seemed pretty good, but of course, that's not very hard to predict. In fact, you could just find out when the server was last booted up and guess all the time down to a few seconds and then try all the microseconds and eventually get in. This one was pretty awesome. I remember this was a real mystery when this came out in 2012. These researchers just went and downloaded everybody's public key from all the HTTPS websites, which was 7 million keys on the internet. They're public information. And then they just checked to see if any of those keys were factorable, where you could divide one key by another and get it and show that they come from the same common factor. That should never happen because if you have like 128, if you have a 1024-bit key, the chance of two of the prime numbers used to construct it being the same are incredibly rare, so that should never happen in 7 million tries. And it did happen 27,000 times. And people wondered, how could this be? Something was extremely wrong here, and many theories were proposed, but the ultimate cause that was determined was it was failure of the random numbers. And the problem is they have code like this. You boot up a device like a VPN device. It has to create a cryptographic key. It just seeds the seed from something like the clock, and then it generates some random numbers. And when you have a million identical devices and boot them up, there's a large chance that two of them will end up seeding at exactly the same moment and get exactly the same random number. That's the problem. There's not enough entropy coming in. And since you didn't really plan your hardware carefully, but just made it in some way, it looks good, this happens more often than it should, that the random numbers aren't random enough. So that was the explanation for this. And so then there's non-cryptographic PR. People use non-cryptographic random number generators all the time when they should use cryptographic ones. MediaWiki, that ran Wikipedia for a while. You can see they even put in the code here saying generate hexy-looking random tokens. It's not very random, but who cares? What does it matter? And of course, maybe it matters. It uses this thing called MT-RAND, which is in fact a Mersenne twister, which is just a non-cryptographic random number generator that produces a predictable series of bytes once you have the seed. So this was not very good. But of course, this is another thing that happens very often in security, is people don't think security really matters. Like they're storing the password in plain text, then they say, all right, they told me I can't store it in plain text, so I'll base 64 or something. Now it's not plain text. It's not much better, but it'll shut up my boss. And it doesn't really matter because this isn't really important. And what tends to happen is you make something in a sleazy, fast way because it's not important, and then it's used for another purpose later until that thing that wasn't very important is in fact now very important, but nobody knows that they have to go back and update the assumptions you made. That happens a lot, especially in Microsoft software. So Cryptocat was a chat client designed specifically for people during Arab Spring to protest their government, because people at that time were conspiring anti-government protests on unencrypted Twitter and risking their lives. And so a guy worked really hard to make an easy to use chat client that was encrypted, and considered himself to have greatly aided those people by having it encrypted. But in fact, his encryption was very bad. He made many terrible mistakes. He got a bad reputation after that. They found a lot of flaws, and here's one of them. And this one here was he has an off by one error in this link. See, if you take numbers that go from 0 to 255 and then round them off and try to get numbers from 0 to 10, they're not going to be even. And so he had an attempt to fix that, and he was off by one. So this creates numbers from 0 to 9 that are not equally probable, not all the numbers from 0 to 9, because of an off by one error. And that means, of course, there's not as much entropy as there should be. This is a relatively small problem. He had 45 bits of entropy instead of 53. There were much larger problems in Cryptocat, and he had to update it quite a bit in response to a serious security audit. Anyway, I got more Cahoots. I see we're right on time here. So let's get rid of this one and go to this one. And we'll do a little bit of plain old math. All right, I'll wait another few seconds, but I think 9 is the number. Apparently so. Oh no, all right. All right, guess that's it. Okay, so which one of these harvests the entropy from the keyboard and the mouse? That's the RNG, the really random numbers. The really random numbers must come from something outside. All right. Which item updates the entropy pool? That is what the PRNG does. It takes those bits that came from the keyboard and mouse and it scrambles them up with something like SHA-1 to make them uniform, and it uses that to update that entropy pool. All right. So what's the praying algorithm for the Mac? It's Yarrow, the older one from Bruce Schneider. All right. And what's the source of random bits recommended on Linux? Random will never stop pumping out data is the one that's recommended. Random is the one I use for the demonstration that actually stops working when there's not enough data in the pool, which is interesting for the demonstration. But the problem is, of course, if your software was running something like encrypted chat and that thing stopped providing bits, your code might keep running and not realize they're all zeros now, or things like that. You know, it's a problem to just stop working. So I got Caitlin twice, and I got Ron. And last, they'll have to tell me who they are if they want points. Aha, here comes a chat message. It may be the secret identity of last. Ah, good. Okay, good. All right. I have your top secret identity. All right. Good. So now I want to do a little bit of plain old ordinary math. I try to do a little bit of this each meeting so it doesn't become tedious. And last time we did, I think, bytes. And now I want to do a little bit more. So this is all from the binary games. And I think we did hex. We got up to hex last time, I think. Let's pick up there, I think. So the hex and modular, that's my plan today, modular 1. All right. So here is hex. So you have from 0 to 15, which is from 10 to 4 ones. This is a nibble. And you call this F. E, D, and C. A is 10. C is 12. D is 13. And so you go. You now have one character for a nibble. So there's your 4 bits, 1s, 2s, 4s, and 8s. And that goes from 0 to 15 or 0 to F. And so now if you have a byte, you, instead of trying to take 128 plus 16 plus 8 plus 1, that's the old way to do this, which is very annoying. The fast way is to do the nibbles separately. The left nibble is 9, 1, 2, 4, and 8, and the right nibble is 9, 1, 2, 4, and 8. So this is the hexadecimal number 99. And the left number is the number of 16s, and the right number is the number of 1s, and that's it. So it is 9 16s plus 9. This is the fast way to get from binary, you go to hex, and then from hex to decimal. Hex sits in the middle between binary and decimal, makes it easy to go both ways and go anywhere you want to go after you get used to it, which is why everybody likes to print out binary data in hex in every product you use. So I've got some Cahoots with the hex on them, and that's binary 3A and 3B. I think we did 3A last time. Let's try it again. All right. See if everybody's. Well, I should mention, someone was disconcerted in the last class. Cahoots grade you not only on accuracy, but on speed. So you can get a high score even if you miss one or something, which can seem like something unfair is happening. But as far as I know, it's not unfair. It's just that it grades you on speed as well as accuracy. Of course, it's an opaque algorithm. I don't really know how they're assigning a score, sort of like CCDC. If they start charging for it or otherwise irritate me, maybe I'll write my own. But it won't be as cute. I'll wait a few more seconds. I think there were 11 at one time. 2 people may have gone to sleep. 5 more seconds. Yeah, apparently no more. Ah, okay, there's 10. All right, I'll wait 5 more seconds. All right, guess that's it. All right. So 0x0, 10 in base 10. That's a hexadecimal number. That's 16. 116 plus 0. All right. I was looking at what other numbers I get. The most popular number is 2. If that was a binary number, it would be 2, but it's a hexadecimal number, so it's 16. All right, how about this one? 2, 1 in a hexadecimal number. That's 33, 2 16s plus 1. All right, how about this, AA? That's 10 16s plus 10, so 170. And that's, oh, I see, it is 170 in base 10. I was going to get it wrong. In base 2, it's this. That's confused. That's what it looks like in base 2, which is very easy. 10 is 10, 10. A is 10, 10. Good. Most of you did better than me. Good. All right, how about this? E1 in base 10. Okay. Okay, that is 225, because 14 16s is 224, and then it's 1 more. All right, so let me record the winners, and I've got 2 more of these. I got food. All right, and I got one, 3B is here. Okay, let's see how that looks. right, I think we got 10 people. All right. Well, I'll wait another 5 seconds. We'll see if we have a 10. Apparently not. Okay. All right, FF in binary. Okay, good. That's all ones. F means you have 4 ones for that nibble and 4 ones for the next nibble. All right. How about AA in binary? All right, we've seen that one before. 10, 10, 10, 10. All right. 192 in hex. All right. Nobody was faster than me. There they come. Good. All right, and that's C0, which is 12/16. 160 plus 32. All right, a popular answer. How about that mess in hex? 1100 0011. Yeah, that's good. To convert binary to hex, you just read the nibbles. The left 4 bits are C, the right 4 bits are 3. You do not go adding 192 and 64 or any of that nonsense. You're wasting your time. These turn into C and those turn into 3. All right. How about this in hex? You should be able to read it right off of that. Looks like a lot of people can. That's it. The left nibble is F, the right nibble is 7, F7. All right. Looks like I got more. A3 in decimal. All right. Good. Yeah, that's it. 163. A is 10/16 and then 3 more. All right. And that's it. Okay. Now I got one more new topic I'm going to show you because I think people did pretty well on that stuff. And it'll move us ahead. So let's look at this, which is modular arithmetic. So let me close some of these things. Okay, modular arithmetic, this is the first one. This is at the heart of all cryptography, because if you have cryptography, you have something coming in like bytes that go from 0 to 255, and you want to encrypt it and still have bytes that go from 0 to 255. So you can't do something like multiply it or add to it, or it would go beyond that limit. You need to do your math on a ring. And that is modular arithmetic that you have to get used to. So Here's how a modulus works. It works like a clock. You just go around a loop. You have 0, 1, 2, 3, 4, 5, and when you add one more, you're back to 0, just like a clock. And so 0, you call that mod 6, I mean, wrapping it on this ring. So 0 through 5 are what you expect, but 6 is 0. Because you take 5 and add 1, you're back to 0. 7 is 1. 8 is 2. They never get any number that is anything other than 0 to 5, 0 to 5, 0 to 5. That's modular arithmetic. You are not working on a number line that goes to infinity. You're working on a ring that just goes around and around and around through the same numbers over and over. You never get any number that is not one of the numbers on the ring. So I go to the next page if my thing would work. Okay, I skipped a bunch. That's all right. So here's modulus 9, 0 through 8. So you have numbers up to 8, then 9 is 0, 11, 10 is 1, 11 is 2. And by the way, one way to do it mathematically is you divide by the modulus and take the remainder. So 11 has 1 9 plus 2. 15 has 1 9 plus 6. That's the mathematical way to do it. So here you go. You can go as high as you want. You can have 35 mod 9. That's 8. Because 36 would be 4 9s, taking you back to 0, and it's 1 below that. So just like in binary, you can learn shortcuts. You can have negative numbers. -1 means you don't go 1, you go the other way. If you go back 1, you're at 8. -2 is 7, -3 is 6. It's a little mind-bending at first, but that's how it works. You can add and subtract. You can even multiply, but you just go around and around that ring. You never get off the ring, no matter what you do. So here's addition. I can take 0 plus 1, and that will give me 1. I can take 1 plus 5, and that'll give me 6. Now I can take 8 plus 3 mod 9. That'll give me 11 mod 9 or 2. Now modulus can be done either before or after the addition. So I can take 15 plus 13 mod 9, and that's 28. And that's 27 plus 1, so the answer is 1. But I could also distribute the mod and have 15 mod 9 plus 13 mod 9, and that would give me 6 plus 4, which would give me the same answer. You can take the modulus. This turns out to be extremely important in RSA. Applying the modulus to things early makes your computation much faster because it makes the numbers smaller before you do an expensive operation like exponentiation. And so now you can do subtraction. 7 minus 2 is 5. 16 minus 5 is 11, which is going to give me 2. I could also take 16 mod 9 to get 7, minus 5 mod 9, which is 5, and that would give me 7 minus 5 for 2. So you get a little bit of a clue here that taking the modulus of these numbers separately is faster than combining the numbers to get a big number and then doing the modulus. And that will come back again. You can have a ring of any size. Here's modulus 4, 0 to 3. So 4 is 0, 5 is 1, 12 is 0, 13 is 1, and so it goes. Here's mod 6. We looked at that already. You go 0, 1, 2, 3, 4, 5, and then you're back to 0. So let's see if you can do some of them. I've got a Cahoot of modulus stuff. Someplace in my mess. Here it is. All right. I see a chat message. A problem with the VM software. Projects, right. Projects aren't late until sometime in February. I think because this class, yeah, not until February 12th. Yeah, nothing is late until February 12th. Good, that's a good question. Now let me see if I can figure out how to get back to the Cahoots. It's one of these tabs. It's this tab. Good, all right. My projector's working better. Oh well, it's sort of random. I got 10. I think that's all I expect. I'll wait another 5 seconds. Oh, okay. 1, 2, 3, 4, 5. I guess that's it. Okay. So what's 8 mod 9? All right, that's 8. 9 mod 9 means you have the numbers 0 through 8. So 8 is fine the way it is. All right. What's 15 mod 8? Okay, that's 7. A lot of people got it. The point of mod 8 is that 8 takes you one complete turnaround, so you can take away any multiple of 8. So 15 is 8 plus 7, so you're going to have 7 is what's left over. You throw away all the 8s, and whatever's left with the remainder is what you keep when you're doing modular arithmetic. All right, what's minus 10 mod 9? All right, division gets a little strange. Another way to look at it is I can add 9 as many times as I want. So if I add 9, it's minus 1. And if I add 9 again, then it's 8. That's one way to get there. It's 8. Or it's minus 1 mod 9, but minus 1 is 8. 0, go back 1, and you get to 8. The answer is 8 any way you cut it. All right. Now, the other one people are getting is 1, and that's from getting the minus sign wrong, which is very easy to do as you get confused. Plus 10 mod 9 is 1. Minus 10 mod 9 is minus 1. And minus 1 does not equal 1 in modular arithmetic. It's the opposite. Anyway, you get used to it. So what's that mess? Mod 9. 10 times 11 times 11. Okay, it's 4. And let me just put up some stuff here to talk about it, because I see some people got it wrong. And I should mention how to do this the hard way and the easy way. So let me make a big thing here. Okay, so the hardest way to do it is 10 times 11 times 11. That's 121, 0. And now you want to take that mod 9. So you would take 1,210 and divide by 9 and look for what's left over, which I would need a computer for. That would get you the right answer. But what's much better is to take this and do the modulus on each term individually. So you take this and you take each term mod 9. Ten mod 9 is 1. And 11 mod 9 is 2. So I take 1 times 2 times 2, and I get 4. And that's what I said a couple times. If you take the modular of each term individually, you will find the math to get much easier. And the difference in things like RSA is enormous. It's the difference between being able to use it and having it so slow that you cannot use it. Anyway, so that's it for that one. All right. And so let me make a record of the winners, which are Dude, Caitlin, and Hi. Okay. And Hi. You're Dude, right? Okay. Dante, right? Good, okay. All right, now I got a few people who didn't tell me who we are, like Y and Hi. Maybe this chat message will tell me. Y and Hi. Okay, good, okay. Good, then I might have all the names. At least I got a lot of names. All right. So I'm just going to close it down. I'll go up to the lab and help anybody that wants to work on projects here. You folks do have time. Some people were asking me about when things are due, so let me just point this out. You've got your score is based on quizzes and projects, and you should already be taking quizzes. You get them online. Up here is the link. You sign into this Canvas server, which is not the City College Canvas server, but my own, and then you'll find quizzes up there to take. And you can take, and then there's projects, which are down here on this page, where you set up various forms of cryptography and send in email attachments to my grader to grade them. So you should be doing these. None of it is late until February 12th, though, but you should already be started reading the chapter, taking the quizzes, doing the projects. But since some people are still adding, I'm not going to punish anybody for being late until after the 12th of February. Yeah, you had a question? Message. Oh, a message. Thank you. Good. Let's see what this message is. Okay, just thanks. Good. Okay, good. All right. You're welcome. Glad to have people along. Okay, I'm going to stop the share and pack up my stuff and go up to 214 for a while. By the way, there's now lab hours. You'll find them on the page. I have a couple of lab